Welcome to Part 2 of Lecture 1 for Radiochemistry. Part 2 focuses on information related to the chart of the nuclides and table of the isotopes, and radiochemistry introduction, which includes some atomic properties, nuclear nomenclature, types of decays, and the limitations of the course, which goes into fundamentally nuclear physics. Radiochemistry terms and concepts are really revolved around the nuclear properties. As we discussed earlier, radiochemistry is an intersection between the chart of the nuclides and the periodic table. So when we think about that in terms of an atom, the chart of the nuclides really describes the nucleus, so the number of Z, the number of protons, and the number of neutrons in the nucleus. In the atom, that's a relatively small area. The electrons, you can think of those as handles that allow us to manipulate this nucleus. That's a much larger area in comparison. And we'll discuss electron interactions and how we can utilize that in separations. Now, the number of neutrons, the number of protons, we use those to define something about a given nuclide. So an isotope has the same number of protons but different number of neutrons. So the element, that's the same element with just different number of neutrons. Examples include carbon-12, carbon-13, and the uranium isotopes that we discussed. But all elements have isotopes. Not all elements have multiple stable isotopes, and that's actually something we're going to find out, is that if you have an odd number of protons, you tend to only have one stable isotope. Another term is isobar. Well, that's where the A, the sum of the number of protons and the number of neutrons, is the same. But what may happen is that you make a conversion of neutrons into protons or protons into neutrons. So these are isobars, are the lines that describe beta decay, electron capture, or positron decay. For beta decay, you have excess neutrons converting into protons, but the total number of neutrons and protons remains the same. An isotone, well, that's similar, that's kind of the opposite of an isotope, where the number of neutrons is the same, but the number of protons differs. And then the final term would be isomer, which is in a nucleus excited state. So just like electrons can be in excited state, nuclei can be in excited states. And we'll learn that, well, neutrons and protons have spins of 1/2, electrons have spins of 1/2. There's lots of similarities that we can use to describe this. Okay, radioactive decay, there's some common radioactive decays that are listed here. There's a full list in your table of the isotopes. Alpha, beta, well, alpha decay, where a helium nucleus is emitted, usually happens in the heavier isotopes. Beta decay, the emission of an electron, where the conversion of a neutron into a proton, building up the periodic table. Positron emission, well, that's where a proton is actually converted into a neutron with the emission of a positron, which is the antimatter pair of the electron. Electron capture, where the nucleus captures K or L shell electron, an atomic electron. And in this case, when that occurs, a proton is converted into a neutron. And then spontaneous fission, which occurs in some of the heavier actinides, where you will have the isotope splitting. And an example here, it's an asymmetric split. Here's an example of californium going to xenon and ruthenium. However, with fission, there's always a distribution, and here's a plot of some fission distributions where we have yield, fission yield versus mass number. So same thing here, fission yield 7%. Fission yield is a very high fission yield. Mass number here goes from about 80 to 160. And two things we notice here, the high Z peak, high A peak is about the same. This is being dictated by the doubly magic tin 132. And then the low A peak, well, where that peak occurs is going to be based upon which isotope is fissioning. So we can see that the 233 is at the lowest and the plutonium-239 is at the highest. Other thing that's interesting about this peak, if we look at ratios of the elements that are formed, or isotopes that are formed, we can get an idea of the parent fissile isotope. For instance, if we look at the ratio of zirconium to technetium, we follow the green for uranium-233. You see that zirconium divided by technetium would be a number greater than 1. If we looked at uranium-235, they're approximately equal. That number would be very close to 1. And then if we looked at plutonium-239, the technetium is much larger, so that number would be smaller than 1. This is a way of identifying information about the fissile isotope that produced the fission products. And then this figure here, where we're looking at uranium-235 fission, the difference is the neutron energy. And the other thing we see is we increase the neutron energy. This valley definitely decreases. We lose a little bit of the shell model, that direction that forms this double hump. We could even hypothesize that at very high energies, we should see symmetric fission. Okay. Another emission, photon emission, also called gamma decay. Right, there's two types of, there's two occurrences where photon is emitted from something that's related to radioactive decay. We'll talk about both of them now. Gamma decay is just the emission of a photon from an excited nucleus. That nucleus can be shown here for plutonium. The plutonium-240 is created. It's at an excited nuclear state. As nature likes to de-excite by emission of a photon, this photon emission does not change the A or the N or the Z of the nucleus. It's just a photon emission, so plutonium-240 goes from an excited state to a ground state. Same thing with technetium-99. M, it's a metastable state, and it will decay to the technetium-99 ground state. X-rays, they're also photons. They tend to be at much lower energy, and this is an electron property. So it's an electron being removed from a lower level, electron coming down, photon emission correlated with that removal. You can also have electrons produced from deacceleration of high energy electrons, XRDs. And we can also, when we have X-ray production, if we bombard a metal with a high energy electron, we can produce X-rays in that method. There's also synchrotron light sources in which electrons are accelerated and held in a ring, and these sources produce X-rays, which we will talk about when we talk about advanced light sources. Here's an example of some X-rays that are produced from removal of K-shell electrons. Electrons coming from the higher level will emit photons while falling to this K-shell. So if we move electrons here, electrons from the L, M, N, etc. shell come down, they will emit characteristic X-rays. Back in 1913, Moseley evaluated this, and he showed that the frequencies are proportional to basically the atomic number. This is what we use today. You do SEM analysis. You're able to determine the element by the X-ray. The chart of the nuclides presents all the isotopes that have been evaluated and examined and are constantly being added to. The chart of the nuclide plots the number of protons against the number of neutrons. We have these gray isotopes, which represent the stable isotopes. It's kind of like a valley. You can almost think of this as a topo map. The data that's presented here includes information on the chemical element, which would be listed here. The nuclide information, for example, spin and parity, 0+ for even nuclides. So all even nuclides are 0+. They're not listed. So helium-4, for instance, is 0+. Helium-6 is 0+. Carbon-12 is 0+. And then for isotopes that are stable in particular, you can get mass information. So if we look at helium, lithium, beryllium-9, boron-11, boron-10, we'll get the mass of those isotopes. And then for the radioactive isotopes, number of data are provided. And these are listed here. They include half-life, decay modes, isomeric states, if there's part of a natural decay series, and reaction cross-sections. Now, by using this chart, I can actually figure out what will be the parent, what a parent will decay to. If I look here, an original nucleus, if it decays by beta, it'll go up this isobar, original nucleus, to a beta minus. If it decays by beta plus, it goes down. If it decays by alpha, it comes out to this direction. So as an example, if I look at beryllium 11, it decays by beta minus, and that decays up to boron 11. Carbon 10 decays by positron emission, and that goes down to boron 10. Some of the primary data that's available is listed here, and this is from the legend in the chart of the nuclides. For any chemical element, you'll see the symbol, the atomic mass, the name, and cross-section data for thermal and resonance integrals. So for a stable isotope, you'll have its symbol and mass number, the percentage of that isotope that is composed of that element. So palladium 108, 26.46% of palladium is the 108 isotope. Now you also have cross-section data, and here we see that the cross-section's in parentheses, and there's two sets. And it's listed here. There's thermal neutron capture cross-section in bars for the isomeric plus the ground state, and then the resonance integrals for the isomeric and the ground state. So for palladium 109, there's what's called an isomeric state, so an excited state. So this is the cross-section for the nuclear reaction of a neutron forming the 109 isomer, and this is the cross-section for the 109 ground state. Continuing with the information of the chart of the nuclides, we have data on the artificially radioactive isotopes. For example, here, neodymium 147. Spin imparities listed, where it says 5/-, that's for 5/2 minus. The half-life is listed, so it's 10.98 D is for days. You have A for years. You can have hours, seconds. And since this is radioactive, you have decay modes, and the decay modes are listed here. So there's a beta minus, so that's a beta minus decay, and there's a number that follows it. And here's a gamma, and there's a number that follows that. If I look in the legend, it says the primary primary decay modes with their energies. It's MeV for alpha and beta, so this is 0.805 MeV. And for gammas, it's in keV, so this is 91 keV. Here are the thermal cross-sections for the neutron capture of neodymium 147 going to neodymium 148 for thermal and resonance. And here's the beta disintegration energy. This little black triangle here shows that neodymium 147 is produced as a fission product from the thermal neutron fission of uranium-235. Now there's also other isotopes which are presented, which are naturally occurring, but they're radioactive. And an example, what we've seen in the early part of the chart of the nuclides, that includes tritium, carbon-14. But here's an example, lanthanum-138. It has a spin of 5+. Since this is naturally occurring, it does occur. Lanthanum has this small amount of radioactive isotope. 0.09% of the lanthanum is the 138. This isotope has an extremely long half-life of 1 × 10 to the 11th years. And again, here's the disintegration. And this decays by electron capture, beta minus. And then gamma, and here are the cross-section information. And this is something called the shielded isotope from the thermal neutron fission of uranium-235. For radioactive isotopes, there's similar data. Again, the mass and symbol number, spin and parity. Some isotopes will have, for instance, this lead-210 has the RAD, that's the historic name, radium-D. The half-life, and again, all the same information, the beta decay energies, the gamma decay energies, and then cross-section information. So that's a N-gamma cross-section information. Some isotopes have more than one isomeric state, so a excited state and a ground state. These are listed by the split isotopes. An example here of xenon-129. On the left side, this side is the metastable state, and on the right side is the ground state. The metastable state has a spin and parity of 11/2 minus. The ground state is 1/2 plus. The half-lives differ, about 8.9 days, versus, well, xenon-129 is stable. The ground state's stable, and it is 26.4% of xenon is xenon-129. Again, decay energy, and then cross-section energy. And since this is a stable isotope, the isotopic mass is listed here. Another example of radioactive isotopes where both the metastable and ground state are radioactive, listed here for tellurium-131. Again, the spin and parity, the half-life, the decay modes, beta disintegration energy, and a fission, this triangle here indicating that it is from the fission of uranium-235. Other data that's presented in the chart of the nuclides on the ends here, as this is kind of, we can use this also as a review. Here's all the data for the elements. Right, so silver, 107.8, cross-section, the cumulative cross-section information. As we see, as we go from silver, we get different silver isotopes as we go up. But this data here, these are the fission yields for these given isobars. So for instance, if we look at the 99 isobar, the fission of the percentage of uranium-233 when it fissions that forms the 99 isobar, uranium-233 is here, is 4.9%. You see it's not in parentheses, that's for uranium-233. Plutonium-239 is in parentheses. So when plutonium-239 fissions, 6.21% of the time, it'll form the 99 isobar. So you should be able to answer this question for other isobars on the chart of the nuclides. For uranium-233, plutonium-239, for instance, if we look at the 104, about 1% of the time, when uranium-233 fissions, it yields the 104 isobar. And for plutonium-239, it's 6.1% of the time. Similar data is also present for uranium-235. It's on the other side. You see, it's just the single data points. So if we wanted to look at the 132, and here's our doubly magic tin 132, 82, and 50. We can even see that it's got slightly darker bars here. 132 occurs 4.31% of the time. Okay, so based upon what we've discussed already on the chart of the nuclides, you should be able to identify isomers, isobars, isotones, and isotopes. For instance, isobars here, we could say that 57, nickel 57, iron 57, cobalt 57, those are isobars of 57. You should be able to identify the daughter from the decay of the following. So if you were given an isotope and look up the chart of the nuclides, you should be able to indicate what is the daughter of that decay. For some bismuth-212, decays with both alpha and beta. And some isotopes, well, lead-208 is stable. You should be able to identify that it is stable. How is carbon-14 naturally produced? Actually, if you read the front section of the chart of the nuclides, you'll see that nitrogen-14 is a target. And if you look at nitrogen-14, if a neutron is added to that, you will get nitrogen-15. So if we take a proton away from nitrogen-15, we get carbon-14, so the reaction must be high-energy neutrons hitting, or one of the possible reactions, high-energy neutrons hitting nitrogen-14, that nucleus then emitting a proton. And then you should be able to do something like identify 5 naturally occurring radionuclides with a Z greater or Z less than 84. Those again, those are the isotopes with the black bars. Here's some other questions. You should be able to identify how many stable isotopes does nickel have? What's the spin and parity of a given isotope? How is plutonium-239 made from uranium-238? Well, if you go to the chart of the nuclides, look at uranium-238, and if I added a neutron to that, I'd get uranium-239. And if that uranium-239 sat, it would undergo beta decay to neptunium-239. And then that neptunium-239 undergoes beta decay to plutonium-239. And that's how we can make plutonium-239. From this, what's the half-life of tellurium-130? If I look at tellurium-130, here's the isotopic abundance. Here's the half-life, 6 times 10 to the 20th years. How does it decay? It's got 2 betas. Well, tellurium-130 decays by double beta decay. And what is the cross-section data? Well, there's 2 data sets here. So this is and you see that the tellurium-131 has an isomeric state. So here's the thermal neutron going to the isomeric state, thermal neutron going to the ground state, resonance to the isomeric state, resonance to the ground state. So this information that's presented in the chart of the nuclides, that can be supplemented by data from the table of the isotopes. And this contains actually much more detailed information. You'll get a mass decay scheme, get information about mass excess, particle separation energy, gamma transitions, and some structural information. So let's see what this looks like. If we were to go to, if you download from the web page the table of the isotopes, you'll get, open it up, you'll get something that looks like this. And if I want to find out some information about an isotope, I can either go to the nuclear chart index or the summary. If I click on one of these, I'll get a list of A's, so these isobars. And for instance, let's look at A of 60. So I can go here and click on A of 60. And what this brings me, this will bring up this information here first. It'll show all the A of 60. So let's say I'm interested in finding out information on cobalt-60. Well, I already have some information here. It'll give me the Q value, which is listed here, the information about the half-lives. Looks like I've got a metastable state and a ground state of this isotope. The spin and parity is listed here. The neutron and proton separation energies. There's a lot of information available. So if I click on this, if I click the cobalt-60, it'll give me a list of information here on cobalt-60 that include the mass excess, the cross sections, references that I can look up, and then towards the end of this I'll get some gamma decay information. So cobalt-60 decays to nickel-60, and the yields of the gammas are listed here. So I see that I get 2 gammas, one at 1,332 keV, one at 1,173 keV, and they're each at very close to 100% yield. So how do I get the yield? Well, I take that number and I multiply it. It tells me what number to multiply by. In this case, it's equal to 1. So if I then click on where the cobalt is listed here, it gives me the decay scheme. And here's much more detail on the decay scheme. So I can see that cobalt 60 has a spin and parity of 5+, a half-life of 5.27 years. It decays by beta. It populates this state 99% of the time. We go to this 4+ state, and then that 4+ state will gamma decay to this state, and then that state will then gamma decay. So that's why we get these two high energy gamma decays from the decay at cobalt 60. Right. Other information that you should be able to utilize from the chart of the nuclides is, here's some equations that we'll go over in a little bit more detail. But one thing we should be able to evaluate is something called the decay constant. From this equation, which this is just the definition of half-life, where the number of half-life is just the amount of time it takes for half of the atoms, or the mass, or the moles of the isotope to disappear. So here's the data for example iodine-131 as a function of time. We use this as just a first-order decay constant, where the number of atoms at any given time is equal to initial e to the minus lambda t. This lambda is the decay constant, and it's equal to log 2 divided by the half-life. So since the chart of the nuclides and the table of the isotope has all the half-life data, we can now calculate the decay constant for any isotope. Okay, and this can be done, as examples are provided here. If I look up some of these isotopes, I presented the data. The decay constant is just log 2 divided by this. I get the decay constancy. And one thing I have to remember is the units. If the half-life's in days, the decay constant's in days. Generally, we like to have the decay constants in seconds. So if I convert days into seconds or years into seconds, I get decay constants that are listed here. So here's an example of how one would do this calculation. Here's the half-life for selenium-75. Log 2 divided by this gives me this value. And if I say, well, in one day there's 24 hours, and in 1 hour there's 3,600 seconds, I recalculate the decay constant in inverse seconds. We can also use this fundamental equation where the number of atoms at a given time divided by the initial amount is equal to e to the minus lambda t. We'll go over this equation in more detail when we discuss decay kinetics. So for now, these are just primary examples. For instance, if I have a question for arsenic-66, how much remains, well, what percentage remains after a given amount of time? So in this case, it's half a second. I can just solve this number directly, because if n is the amount at time t, and naught is the initial amount, well, that's just going to give me a percentage. The half-life of arsenic-66 is 95.6 milliseconds. The decay constant is log 2 divided by 95.6 times 10 to the minus 3 seconds. So I plug that term into here. There's my lambda, there's my t. This value is 0.0266 or 2.66%. So after around 5 half-lives, very little of that isotope remains. I can also use this to answer a question, something to the effect of, how long would it take to decay 90% of a certain isotope? In this case, 90% of zinc-65. What we have to remember, if we talk about a decay of a certain percentage, 90% decays, that means 10% remains. So n divided by n naught is equal to 0.1, 10%. I know the half-life is 244 days. Log 2 divided by 244 days is equal to 2.84 times 10 to the minus 3 days. 0.1 e to the minus decay constant times t, solve for t. Equation, we rearrange the equation. We get this, t is equal to 801 days. examples provided here, and I also provided an example for if you have 1 gram of selenium initially, how much will remain after 12 days? Well, the half-life is 5.8 days. So here's my decay constant. I plug in my equation, 1 gram, e to the minus lambda t, and I can get an answer straight from here. And I can use this, it doesn't matter if it's a gram. I can say how many atoms of selenium, how many would I have remain after 12 days? Well, from this, by inspection, I can see that 37.6% of the selenium decays, and I can just solve it. But I can solve it by plugging, as opposed to 1 gram, I can just put in 10,000 atoms. Okay. As a way of closing out this lecture, we want to talk about nuclear force or forces in nature, because there's 4 main forces in nature, right? Gravity, and we're familiar with that. Electromagnetic force. There's 2 forces that actually deal with radioactive decay: the weak interaction and the strong interaction. Say the weak interaction is responsible for beta decay, and the strong interaction is actually something that defines some of the nuclear properties. So for radiochemistry, these 2 forces are somewhat important. And here's a table that kind of gives you an idea of the forces, their relative strengths, and their ranges. As we see, the strong force is basically on the size of the nucleus. The weak interaction is even smaller than that, while gravity and electromagnetic are a little bit further ranged. The boundary of the course that we're going to discuss is really particle physics. We won't go much into particle physics. However, the tools and concepts such as accelerators, which are used for exploring radiochemistry at higher energies, you start understanding particle physics. Well, for particles, they tend to be classified as fermions or bosons. Fermions obey Pauli principle. We're familiar with these. They tend to have half-integer spins. Electrons, protons, and neutrons are fermions. The reason that this is important, as chemists, we're familiar with electron behavior and how electrons behave through the Pauli principle. Neutrons and protons do the same thing. When we get to the shell model, the fact that these neutrons and protons are fermions, like electrons, you can utilize that to understand something about nuclear properties. Bosons, they do not obey the Pauli principle. They have symmetric wave functions and integer spins. An example of that. When we also talk about particle physics, we can explain some aspects of particle physics using the Standard Model. 2 aspects of the Standard Models are force carriers, these leptons, and then quarks. One of the things that we want to look up, think about when we talk about quarks, is when we think about beta decay, we're often converting either a neutron into a proton or vice versa. And you can think about that at a level with the quarks, where we actually do interchanging of quarks. Now, if I look at the charge, and let's focus on the up quark and the down quark. If I look at their charges, I can see that 1 up quark and 2 down quarks, that's 2/3 minus 2/3, that would be 0. So a neutron would be composed of 2 down quarks and an up quark. Where a proton would be 2 up quarks, right, plus the negative 1/3, that'd be a charge of 1. So you should be able to use this information, answer questions like, okay, what are the quarks in a neutron and a proton? The review of the topics that we just discussed are presented here. These can also be used as part of the study guide for any tests we have related to this presentation. So we went over the history of nuclear physics research, discovery of radio elements, the methods and the techniques that were used, going up to when a new element was then used as a target, to atom at a time chemistry, types of radioactive decay, including some discussion on X-rays and gamma decay, which are photons that are emitted, although one comes from the nucleus and one is due to atomic electrons. We discussed the utilization of the data presented in the chart of the nuclides and the table of the isotopes. utilize fundamental decay equations, and identify common fission products.
Some examples you should be able to answer based upon this presentation are shown here. What are the course outcomes? Well, the course outcomes are understand, utilize, and apply the chart of the nuclides and table of the isotopes to radiochemistry and nuclear technology, understand fundamentals of nuclear structure, understand chemical properties, particularly radioelements, comprehend nuclear reactions and how isotopes are produced, comprehend and describe radioactive decay, the different types of radioactive decay, understand how radiochemistry is used in research and modern topics in radiochemistry. Discuss the discovery of radioactivity in 1896, Becquerel, Marie, and Pierre Curie. So both these people who discovered radioactivity have units of activity named after them. They used a uranyl sulfate salt that was exposed to sunlight. They wrapped it in paper that had photographic plates on it, so they had the salt, photographic plate, then wrapped it in black paper so no more light can get in. When they opened it up and developed the photographic plates, it revealed images of the uranyl crystals. Initially, Becquerel believed that the crystals absorbed light, then phosphoresced. It was later shown that the activity, the photons, were actually coming from the material themselves. And in 1903, the Becquerel and the Curies were awarded the Nobel Prize for this research. It's also interesting to show that even though Becquerel received the Nobel Prize for this, his initial hypothesis on what was occurring was incorrect. Discuss the first man-made nuclear reactor. Well, in December 2nd, 1942, the reactor went critical, and it was called the Chicago Pile. It was under the direction of Enrico Fermi. It was famously initially built underneath the stands of the football field of the University of Chicago. They at one time had a very good football team, and it was the chancellor of the or president of the University of Chicago disbanded the football team in the late 30s. So the area was open. They built this first reactor. It was a graphite moderator reactor. It had natural uranium, tons of uranium, including uranium metal and uranium dioxide. This was called CP1, or Chicago Pile 1. It was moved out to a forest south of Chicago. It was called Chicago Pile 2. This area where it was moved to eventually became Argonne National Laboratory. Another question you should be able to answer is, what are the radioelements? If you evaluate the periodic table, there's a break in the behavior of the nuclear property of elements at right around bismuth. All the elements that are heavier than bismuth, greater than 83 protons, are radioactive. So from polonium all the way up to element 118, so all those elements are radioactive, and they contain the actinide elements. There are two elements that are under bismuth that are only available as radioactive isotopes. Those are promethium, number 61, which is a lanthanide, and technetium, which lives right in the middle of the periodic table, element number 43. And these were discussed in the lectures, and as a final topic, we may have a paper that discusses why technetium is radioactive that you can evaluate. You should also be able to discuss what are the different types of radioactive decay. There's alpha decay, which is the emission of a helium nucleus from the radioactive isotope. Beta decay, which is the emission of an electron. Gamma decay, which is a de-excitation of an excited nucleus through the emission of a photon. Positron emission and electron capture are competitive reactions in which the excited nucleus emits a positron, and this converts a proton into a neutron, moves down the periodic table, as opposed to beta decay, where a neutron is converted into a proton and it moves up the periodic table. Electron capture, the nucleus captures generally a s electron or or a K shell electron from the atomic electron orbital. This converts a proton into a neutron, and the element moves, and the isotope then moves down the periodic table. There's also spontaneous fission for some of the heavier isotopes, where the nucleus will spontaneously split, similar to neutron-induced fission that runs the reactor in uranium, and also plutonium has that behavior. There's other methods of radioactive decay that we'll discuss. These include double beta decay. There's examples of carbon-12 emission, carbon-14 emission. These are smaller probability emissions, and they will be discussed throughout the course. And what are some references on the information of isotopes? And these are important references for the course. One is the chart of the nuclides, and one is the table of the isotopes. And throughout the course, you'll be using both these references for discussions on nuclear material and questions related to the decay of isotopes and the properties of the radioelements. So finally, when you've completed this lecture, please provide comments on the blog and respond to PDF quiz for Lecture 1. Please provide a comment on the blog when you've completed Part 2 of Lecture 1 and respond to the PDF quiz on Lecture 1.